Be perfect, please. Excellent. Okay, well, welcome everyone. And yeah, thank you for joining our collaborative webinar. We've been looking to put a positive spin on the current situation with this web series. We've combined the powers of both the Danish and the British NGN to serve up some really interesting content for you to chew on today. But before we start, I'll give you some background. So my name is Max McFarlane. I'm the current technical lead of CIGRE UK NGN steering committee. And being a part of CIGRE has given me some really insightful experience. I've learned so much already from just a few engineers and been given so many opportunities that wouldn't have otherwise been readily available. When I'm not volunteering as technical lead, I work as a graduate consultant at TNEI Services, and we're an independent strategic energy consultancy working to provide technical, strategic and environmental consenting advice to those working within the energy industry. Most of the time you'll hear me proclaiming about our mission to roll out statistically robust methods of deriving insight from data. But you'll also find me working on D&O investment strategies to support our international fight to achieve net zero. And yeah, what better way to fight for this goal than with the wizardry of offshore wind? And today's a fine example of just some of the benefits of CIGRE, as this series of technical presentations in the form of webinars has brought together honestly, some really great minds to share some invaluable knowledge. So yeah, as today we'll be focusing on offshore wind technologies. We'll have two speakers from each respective NGN group, Lorenzo Zeni and Troels Sørensen from Ørsted Offshore in Denmark. And finally, Dr. Stephen Blair from Synaptec and Dr. Jingyi from Cardiff University. So I'll just take this opportunity at the moment to let you all know that we will mute you all from the start. I'd like to encourage you to use the chat box for any questions that you may have. And throughout the webinar, each speaker will have 10 minutes to deliver the presentation, and then each will have a 5-minute question and answer session. I'll look to get as many of these questions answered for you as possible, time permitting, but for any that we can't quite squeeze in, please send them through to the email address that's linked at the start of the chat thread. So first, I'd like to introduce our representative of the Danish NGN, Daniela Pagnani. Daniela is completing her innovative PhD studies of black start mechanisms in offshore wind farms at the Aalborg University in Denmark with the support of Ørsted. She previously completed her master's in HV engineering at the same university and her bachelor's in industrial engineering at the Sunny University of Cassino and Southern Lazio in Italy. You have the virtual floor, Daniela.
Thank you very much, Max. Can you all confirm that you can hear me?
Yes.
Perfect. So thank you, Max, and welcome everybody. Thank you for being here and joining us today. My name is Daniela Pagnani, and I'm here to tell you a bit more about CIGRE NGN Denmark. Next slide, please. So here are some facts. We are quite a new NGN. We had our kickoff in March 2019, so a bit more than 1.5 years ago. But already we count more than 50 members. That was our 2-year objective. In creating our NGN, we got support also from other NGNs, such as the UK NGN that we're here to thank today. We also had a great support from the Danish CIGRE National Committee that was interested in having the word of CIGRE shared to students and young professionals in Denmark. And here I have the names of some of the people representing Danish National Committee of CIGRE. And as you can see, they are professionals from the most relevant companies and university in the energy sector in Denmark. And also Troels that is here to present today. Next slide. This is us. We are the steering committee of NGN Denmark. We are all students and young professionals from different companies in Denmark, where Hamza and Chian are respectively chair and vice chair of our NGN. And it's interesting to note that the majority of us is girls, so it's very, very nice and a bit uncommon in my opinion. As you can see, we have Aalborg University and Ørsted leading the way, and this is a good part of the collaboration. Next slide, please. Yes, so as an organization, we want to focus our scope in 6 different areas that we have here identified, and I've written down in this slide. And the areas go from reflecting the need of young engineers in the power industry, something that we felt ourselves somehow, to represent CIGRE as an organization, and to furthermore offer networking and professional opportunities. And as a member, you will enjoy all of this. That is our effort. And as a volunteer of the steering committee, I can say that we are proudly doing our best to complete something in all these areas. Next slide. So for a bit of promotion, I can say that we offer different benefits in being a member of CIGRE NGN Denmark. And these opportunities go from knowledge sharing and dissemination, professional networking, and personal development. And you will see that we are a variegated tour of different people, and we have different scopes. So you could see that being a member of us. Next slide, please. And in our pipeline, we have different events that we want to share with you, and this is a glance of our activities. First and foremost, this is the first time we announced it, is another webinar that this time will be in collaboration with Jan CIGRE, the Netherlands. And the scope is offshore energy hubs. It's brand new information, and we're still in the planning phase, but we have a date, which is a bit more than in a month, the 11th of November. So stay tuned for more details. And from DK side, Ørsted is leading the way together with NGN. And as soon as we have more information, we will start the promotion. Next. Another event is in collaboration with Aalborg University and NGN, and is the visit at the substation of Vestra Hesting in North Jutland. And this is very relevant for all the power system engineers that are interested, for example, in HVDC, as this is the substation connecting the Kontiskanta HVDC link with Sweden. So I think it's quite an exciting opportunity that is not very easy to get every day. Next. Also, another visit correlated to HVDC is the visit at the Cobra cable, which is organized by NGN. This was originally planned for April 2020, but as all we knew, we were in the middle of Corona lockdown at that time, so we want to plan it as soon as the COVID restrictions are lower, let's say, come back to place. And the plan is to visit Fredericia, headquarters of NGN, and Andrup in South Denmark. Next. Then Avalor Power Station and Wind Farm visit. And this is led by us in Ørsted, and is an event to visit Avalor Station that is located a little south of Copenhagen area. And it comprises of both an offshore wind farm and a combined heat and power station. And it will be a technical tour inside the power station. Next. Last but not least, Vestas nacelle production visit. And of course, this is organized by our people in Vestas, and it will be a technical talk and tour with the possibility of visiting the manufacturer, visiting the how the power equipment is manufactured. And of course, all these events are need to be somehow physical, so we will have the actual announcement when the date is visit. But as you can see, our brains are still working no matter the lockdown. So next slide, please. Is just to conclude and say that if you want to hear more from us or you want to join us, the registration link is on the next generation page of our national CIGRE page. And you can also follow us on Facebook and LinkedIn. And also questions are always welcome, both on social media or on our pages or on our emails. Thank you very much.
Thanks, Daniela. The floor.
Yes, can everybody hear me?
Yes.
Good. Well, thanks a lot for the invitation to talk in this interesting webinar. I am Lorenzo from Ørsted in Denmark. I'm a senior power system specialist with Ørsted, and today I'm going to give a presentation which is maybe not so much bringing Ørsted stuff to the table, but maybe more of a general overview about HVDC technology and offshore wind. So next slide. Yeah, I'm gonna split the presentation in 3 parts, talking about the past, the present, and the future, so to say. So I'll briefly talk about where we come from and then where we are today, and then give some maybe hints for directions for the future. Next slide. Yeah, so where did we come from? What are the drivers for utilization of HVDC technology for offshore wind? Clearly, the fact that wind farms are getting larger and larger, and that the distance to the point of connection is also getting larger and larger as the sites closest to shore are depleted or not used because of visual impacts. The HVDC technology has become, in the last, I would say, 10 years, a feasible solution. And also because the technology, the VSC-based HVDC technology has matured significantly, although it's still, let's say, relatively young. It's 35 years technology. And it has also low transmission losses compared to an equivalent AC solution. We know that when it comes to AC transmission, with optimal compensation on both sides of a cable, there is a limit, a technical limit, beyond which you cannot go if you want to transmit some power in terms of length. But there are solutions with intermediate compensation to extend the range. So in the last years, we have seen a situation where the economic breakdown between the two technologies, AC and DC, the break-even point has not been, let's say, a clear distinction between one or the other, but it's more of a gray zone where both technologies are feasible for the distances that we're talking about nowadays. Next slide. Yeah, and what happened until yesteryear in the development and application of this technology to offshore wind, we have seen that TenneT in Germany has used this from the very start from their projects in the North Sea, and we have observed a steep learning curve with delays and unavailability. We have seen very large platform sizes, and a solution that includes separate HVAC platforms together with the HVDC, which is maybe not the most cost optimal. These are maybe among the reasons why other TSOs and developers have been a bit reluctant to use HVDC, but I think it was a path that was necessary. Somebody had to take it because the industry did have to go through some kind of learning curve to make this technology fully ready for offshore transmission. We've also seen significant development of grid codes at a European level for HVDC, and research activities spanning all fields from proof of concept at the beginning to large HVDC grids and HVDC breakers more recently. Next slide. And where are we today? I think I've tried to point out the most recent developments here, the most interesting recent developments. One is that for the first time last year, developers actually were awarded CFD support in the UK by applying HVDC technology to their wind farms. And I think that's a very important step for the industry because it shows that it can be done outside the German North Sea. We have also seen at the same time the development of more optimized concepts without the HVAC separate platforms. And we've also started to see national implementation of the HVDC grid codes. So the European legislation, so to say, has been cascaded down to the countries, not everywhere yet, but it's an ongoing process. And we've also seen recently, at least in some areas, more concrete talks about hybrid transmission, which is kind of the next step. So an asset that combines transmission between countries and generation from of wind power from offshore. Next slide. In terms of technology, the state of art today, I would say, is a symmetrical monopolar system at 320 kV DC plus minus, and around 1 gigawatt. We have seen examples in the North Sea in Germany with around 960, I think, while in the recent CFD round, we have seen powers of 1.2, 1.4 gigawatts. I think by now we can say that it's a proven technology with an acceptable risk level. Of course, different people have different opinions there. That's my opinion. The capability to deliver on current grid code requirements is proven, I believe. But let's say from a supply chain perspective, we are still far from having systems that are like the HVAC systems, because we have what I put in between inverted commas here, standalone systems from single converter suppliers, in the sense that we have not seen any interconnected systems, at least in Europe. And the HVDC system is always something that is developed by one supplier, assuming that all the converters in the system are from the same supplier. So we are far from a plug and play, so to say. Next slide. Yeah, where are we heading to? When we look into the future, I went from statements to question marks, because of course I have no crystal ball, but some points to think about are higher voltages and larger capacities and better redundancy. We've heard that TenneT Holland actually plans to develop 2 gigawatt connections at 525 kV, and in terms of redundancy, if we want to go up in power in a country like the UK, we would need to switch to bipolar solutions in order to comply with the loss of in-feed limits. And this is, I mean, with different megawatt levels, but it's applicable pretty much anywhere. Fully interoperable system, as I said, we are far from a plug and play, and that is something that from a supply chain perspective is quite important. In order to be able to reduce costs, it would be ideal to be able to have a situation where you can, based on a generic specification, source converters from different suppliers. Yeah, there could be further changes in technology. We have seen recently the proposal of diode rectifiers, for example, offshore, to reduce the footprint of the offshore platform. We have seen also a lot of research about DC collection grids, and there may be others that I am not aware of. Hybrid transmission will in my opinion, be the next step towards the deployment of HVDC technology offshore, because that's the natural first step. But then we will probably move towards fully interconnected systems with a proper offshore grid, so to say, and a more widespread network to collect the wind power and also transmit energy between countries. And then if one goes all the way into the future, one might even argue that HVDC could become the backbone of a 100% renewable energy system, but also even going a bit more extreme, once power electronic devices needed for DC become reliable enough and cheap enough, one could even stretch it all the way to say that the whole grid, from generation to transmission to distribution, could possibly become DC. Yeah, there are some talks in this direction, but it's maybe farther into the future. Next slide, which is the final slide. Yeah, these are just a few relevant challenges that I think are interesting for the future. You can, of course, append to this list, but it's the first four that came to my mind. And one is the size and weight of HVDC platforms. When we go offshore, and we increase voltage levels, it's quite challenging to fit these converters into the platforms. And you know, there can be different solutions. There can be development in the supply chain of installation vessels and construction yards. There can be energy islands avoiding platforms completely. There can be different insulation means than air. So there's a range of solutions, but this remains a challenge when going offshore. And then generic functional requirements to enable interoperability is also something that should, in my opinion, happen very soon, but maybe it will not happen that soon. And there should be an effort here to make sure that we have a flexible supply chain in the future to pick from, because that's what allows to deploy stuff quickly and at a reasonable cost. And then there's also the control of converters enabling a 100% renewable energy system. I think when we go to 100% inverter-based generation, everybody knows there can be control challenges because everything is power electronics, and even in applications already commercial, like the German North Sea connections. There are fields where maybe some parties, some suppliers have a proper understanding of technical requirements, for example, during faults, but it's not widespread in the industry. This knowledge is not widespread in the industry to a sufficient level, in my opinion. And then there's a deployment of cost-effective HVDC breakers that will be probably needed if we go for very large offshore grids based on HVDC. This was my last slide. I hope it was let's say a good overview, and I'm happy to, if you go to the next slide, I'm happy to answer any questions. And here is also my email address if you want to reach out to me.
Excellent. Thank you, Lorenzo. I can understand that must have been difficult with all the perhaps NDAs that would have been necessary, or omission of sensitive information. But yeah, that was really great in terms of giving us a good overview of what's necessary. I picked up a few questions in the chat box. The first being, how can we overcome the disadvantages for the converter overloading, such as the many issues with the cooling system, especially where temperatures are very high, and the disadvantages of multi-terminal network connections?
Wow. I mean, converter overloading, yeah, I mean, it's power electronics, right? So they do not really have a lot of overloading capabilities. They are not synchronous machines, and we do know that the cooling system is crucial to ensure that we can get as much power out of the converters as possible. But yeah, I'm not really sure where this question was going to. In terms of multi-terminal HVDC connection, I think the biggest challenges there will be regulatory, because we see that we struggle even to let's say conceive a working system for an interconnector with wind in between, due to market challenges and due to different regulatory regimes in different countries, and so on. So I think from a technical perspective, we are actually ready, to be honest, for an interconnector with wind. But from a regulatory, we are not. And if you take the next step and go to multi-terminal, it becomes even more complex.
Yeah, that definitely makes sense. I think that's sort of
for the multi-terminal, for the mesh multi-terminal grid, one could argue that from the technical perspective, there's also the DC breaker challenge. There's been quite some leaps forward lately, but we are maybe not yet there for an economically efficient solution.
Okay, thanks for that. I think that sort of answers the next question as well, which we don't seem to have time for. But it was generally just what are some of the main reasons for delays in large HVDC connected projects? So I suppose, in a sense, the sort of regulatory bottlenecks would sort of contribute to that. Yeah. What I'm going to do is, Lorenzo, I'm going to send on these questions to you from each of the individuals for you to chew on and to reply back to, because I think just in terms of timing we need to move on. But thank you very much for that. That was fantastic.
Thank you.
Okay, so next up we have Troels Sørensen, also from Ørsted in Denmark. Troels, you have the virtual floor.
Thank you. And can you hear me?
Yes.
Thank you. My name is Troels Stybe Sørensen. I'm the Senior Chief Specialist in Ørsted Offshore Electrical Systems. This is the part of Ørsted that deals with the grid connection systems for our offshore wind farms. So in this presentation, I strive to give you kind of an introduction to our world in Ørsted Offshore Wind. Yes, the next slide here. Kind of a high-level fly into Ørsted at a corporate level. At a corporate level, we have 3 business units. We have offshore, which is offshore wind, including storage, power to gas, and batteries related to offshore wind. We have onshore, which includes onshore wind and photovoltaics. The latest development as of yesterday was the announcement of investment decision on a 367 megawatt wind project in Texas called Western Trail. And then we have markets and bioenergy, which is basically traditional combined heat and power plants, which today is fueled almost exclusively with biomass and waste. And then you can say the market interface of the company trading power and heat into the market. There are about 6,500 employees in the company altogether, and there's also some financial data here, and they are good, by the way. Next slide, please. Some 10 years ago, Ørsted made a strategic decision to transform from a traditional power company into a renewable power company. And this journey has actually been quicker than originally anticipated. So now, today, we have actually reached about 90% of the power and heat generated is green. And we are also ahead of the curve compared to the global energy sector with regards to CO2 emission targets. Next, please. So if we focus now on Ørsted Offshore, these are the markets that we are active in today. It shows both the offshore wind farms in operation, those are under construction, and those that are in the development phase. Until today, we have completed 26 offshore wind farms with 1,500 wind turbines in operations. Total 6.8 gigawatts of capacity, and there's another 3.1 gigawatt in construction. In this part of the company, there are 2,800 employees. This includes about 900 in engineering, and out of that, we are about 200 in electrical systems. And overall, actually, I don't know, but my guess is that there are around 300 to 400 electrical engineers in Ørsted today. This is actually a relatively large in-house engineering capacity for an offshore wind farm company, and actually also for power generation companies as they are organized today. Next slide, please. And the reason for this is that Ørsted builds on a business model where we call it a strong integrated end-to-end model. It includes these 4 steps: development of projects, build the projects, operate the projects, and also own the projects. And we try to hold on to all the key engineering competencies that are necessary to control each of these 4 steps. Most other companies in the industry and also in the generation industry in general have much more outsourced these same technical competencies. Next slide, please. This slide gives you an overview of our journey from the first 4.5 megawatt offshore wind farm back in 1991. We built the first large-scale offshore wind farm in 2002 with 82 megawatt Vestas turbines called Horns Rev 1 in Denmark. Also shown here is the 660 megawatt Warning extension, which was completed in 2018, where we used Siemens Gamesa 7 megawatt wind turbines and Vestas 8.25 megawatt wind turbines. And on the right-hand side, we just shown the 1.2 gigawatt Hornsea 1, which uses 174 Siemens Gamesa 7 megawatt wind turbines. This also shows you that for the last 10 years, the company has been focused on this green transition and has used what we call an industrialized approach to planning and executing a pipeline of offshore wind projects. The first 20 years of this period was more project by project, and to be honest, I don't think that we really knew if there would ever be another wind project. But since 10 years, this has been one long stretch of continued and growing activity. Next slide, please. So what does this mean for grid connection systems? Well, actually, grid connection systems are somewhat overlooked. Often it's a lot of talk about wind turbine sizes and overall wind farm size. The transmission asset, the grid connection system, well, that's just part of it. We think, of course, it's the most interesting and important part, but that's probably just how we are. The first offshore wind farm I mentioned before, back in 1991, that was simply a connection to land with a 2-kilometer, 10-kilovolt submarine cable connecting into an existing distribution system substation on land. The London Array project, on the other hand, in 2012, I think, was already 630 megawatt, connecting the wind turbines at 33 kilovolts and using 2 150 kilovolt offshore substations connecting to land with 4 parallel 50 kilometer long export cables to a large dedicated onshore substation. And the 1.2 gigawatt Hornsea 1, which was completed earlier this year, it also connects wind turbines at 33 kilovolts, and it uses 4 220 kilovolt offshore substations and 3 parallel export cables to land, about 120 kilometers, and another 40 kilometers on land to reach a large dedicated onshore substation. And at the right-hand side is the next project. It's the 1.4 gigawatt Hornsea 2 projects. In this project, we connect the wind turbines at 66 kilovolts. There's only 2 offshore substations, but still 3 export cables going to land and connecting also over a distance of around 150 kilometers. Next slide, please. So what has made this possible? Well, as a lot of things. And one thing was the very clear cost reduction targets that were put up by the UK government, I guess around 10 years ago as well. As I've experienced that essentially forced the alignment of development across the industry, including a lot of innovative effort. That made a huge difference, and it was possible to reduce the cost of electricity dramatically, something like 60% over a period of these around 10 years. Another element has clearly been the development of even larger wind turbines, as you can see at the bottom. Larger turbines reduces key cost elements like foundations, for instance. That's really something that contributes to reducing the costs. Ørsted has been heavily engaged in this development, obviously in many of these areas, including the development of high-capacity grid connection systems, 66 kV array cable systems, and very large offshore substations. Next slide, please. The development doesn't seem to stop, I'm happy to say. If you look at the projections and even the firm political commitments for offshore wind towards 2030, they are really impressive. We're looking at an annual growth rate of around 20% or 12 gigawatts per year. This week, the UK government announced projections in this period 2030-2050 in the range of 40 to 75 gigawatts of offshore wind. So I think it's safe to say that these are very good times to be an electrical engineer involved in offshore wind and transmission assets. I have 2 slides more, if I could have the next one. No, sorry, 3 slides more, I think. This is then the translation into what it means for our projections as a company. Right now we are at these 10 gigawatts of installed capacity, and we are aiming at increasing to 30 gigawatts by 2030. So now I have 2 slides left. Next one, please. And these last 2 slides is just some words on how we look at people development in the company. It's something that Ørsted has developed a very conscious approach about. We consider people as the key asset to be able to support this success and continued growth. So we build on people. We're very conscious about it. And we're also very conscious about the importance of having an inclusive environment and supporting creative people in the company. Next slide, please. As part of this, we've also developed a structured career path, working in 3 main groups as kind of a specialist career path, where people like Lorenzo and Daniela and myself belong. And then we have a project management career path, kind of obvious what it means. And then we have a general management career path. It doesn't really suggest that you enter into this and then you're stuck there forever. It's perfectly possible to change between the career paths. But it's one of the things that we have learned when growing it to be an international company. That is actually very important to be able to outline how people can move career-wise, both upwards and horizontally, and maybe even downwards if that's what it takes. And that, I think, is the end of my presentation. I'll be happy to take questions.
Thank you, Troels. Yeah, that was really interesting. There's a good few questions here. I think first of all, we'll go with, when do you believe we'll see the first subsidy-free offshore wind farm if there hasn't been one already?
I think that's easy to say because Ørsted has actually already won with subsidy-free bids in German projects some years ago. And so that reality is already there in some markets.
Great. Okay.
Maybe the slightly longer answer is that there's always a discussion around what is subsidy-free. The German market is a little bit special in the sense that the transmission assets, to a great extent, is actually built by the TSO tenant. So maybe it doesn't translate easily between markets. The situation would be different in the UK, for instance. Okay.
Yeah, and I think most of the projects, or all of the projects that you mentioned there, were using AC cables to shore.
Yes.
And obviously we've been discussing HVDC, but do you believe that HVAC connected wind farms still have a big future in large scale offshore wind farms rather than HVDC? Or do you think it's just going to be full scale HVDC in the future?
I think it's going to be a combination. In a very pragmatic mindset, offshore wind farms will be grid connected with technology that makes sense, both technically, but clearly also what is cheapest. So I'm convinced that we are going to see a mix in the future. If we look at wind farms that are relatively close to the coast, then there's no point in using HVDC unless there are some really specific circumstances. So I don't think it's an either or. It's going to be a combination, and most likely it's also going to be a combination of AC and HVDC connections to groups of wind farms. To my mind, it's probably a lot better to think of kind of an organic growth where future offshore transmission networks will grow system by system in whatever combination makes best business case.
Yeah, of course. Okay, yeah, I think that's all we have time for in terms of questions. For those of you that still have questions, could you please ping them to the email that's at the start of the chat? Thanks again, Troels. That was really interesting. Thank you.
Sure.
Yeah, so before we move on to the next speakers, I know I've gone off script a little bit, but I thought it would be better just to move this section round just to introduce the those from the British NGN. But I'll give you a brief introduction of the team that's behind the British NGN. But generally, the body of CIGRE Global is an international professional organization with a strong drive for collaboration and facilitating technical exchanges in the energy industry. And as maybe some would say that electrical engineering is an aging profession, CIGRE has sought to fill the knowledge gap by creating the various NGNs and thereby providing young engineers with networking opportunities and resources to expand their knowledge. So we quite often say that the NGN is the gateway to CIGRE. Yeah, so first I'd like to give a special mention to the team as a whole, who without their help, these knowledge sharing sessions and many other really exciting events wouldn't be possible. We don't have time to go through each and every one individually, but I'd like to highlight that we do really have a great mix of professionals that are really hardworking and are always keen to bring value to our members. The UK NGN has been running for over 10 years now, with an exemplary split between industry and academia. And generally, yeah, there are quite a lot of benefits with joining NGN. And I think the most important ones to highlight here are that you can make new professional contacts in the power industry, and you can develop your soft skills, such as working in a team, communication skills, and time management, etc. But it also opens up the opportunity to increase your technical knowledge base with sessions like this today. So really the work that you can do with the body as a whole, you can sort of helps you move towards your personal and professional development goals, especially if you're looking to, say, apply for chartership, then that ticks a good few boxes for you. Yeah, here's a brief list of just some of the events that have gone on over the last couple of years, including like site visits and networking sessions, technical forums, and yeah, there's loads more where that came from. You can get more information about all of these events on our website. They go into much further detail. But I'd just like to highlight a couple. Just before the delight of lockdown hit us, we held the Young Members Showcase competition. And this was to bring together young minds and provide them with a platform for them to be able to showcase their work, and the chance of winning a spot at the International Paris Sessions, which were held in August there. And obviously they were not held in person. The Paris Sessions were held online, and it hosted tens of technical seminars and brought together hundreds of papers for collaborative debate. And it's quite interesting because it's not like a regular seminar with a one-way channel of communication. All those papers are distributed among the folk that come along to the session. They read them beforehand, and then they're asked to present the questions throughout the entire session. Yeah, so next year we'll have the centenary session that I'd advise everyone to keep an eye out for. It's sure to be a doozy. In a couple of weeks, we'll have the next webinar in our series, in the UK NGN's webinar series, with the theme of optimizing power transmission and distribution from the sky to the sea. So be sure to sign up for that soon, because I know that one's filling up really fast. And one last thing I'd like to mention is that yeah, I'd like to give you a heads up that we're just going to relaunch our mentoring program, which has been running for a number of years, but we're really looking to scale it up now. So those of you that are on our mailing list, keep an eye out for this too. And if anyone else wants any more information, then please feel free to give me an email. Thanks. So right now, I'll pass over to Dr. Stephen Blair from Synaptec, and I'm sure, Stephen, you're going to take control of the presentation. So I'll stop sharing my screen and you can do so.
Okay.
Okay, I was just double checking you're there. Approve.
Yep.
Excellent. Thank you, Stephen. You have the virtual floor.
Excellent. Thank you, Max. Oh, should I just share the presentation from my side?
Yeah, sure. Go for
Okay.
that. Yeah.
Right, that's fine. In that case, I don't need control, I don't think.
Okay.
2 seconds. Okay, hopefully that's worked. And
yep, we can see that.
Okay, great. Okay, so my name's Stephen Blair, and I'm with Synaptec, which is based in Glasgow in the UK. And I've just realized this is automatically proceeding because I'd pre-recorded it. So let me just bear with me.
Yeah, no problem, Stephen.
Right, 1 second, sorry. Yeah, sorry, this was slightly badly prepared, but I'll be ready in just a moment. Okay, so hopefully I've now removed the pre-recorded stuff, and I'll just share again. Well, many years of playing first-person shooter games helped with the agility required to do that quickly. So, right. So
I can hear the mouse whipping around. Yeah, thanks, Stephen.
So thanks again for joining. I'll try and speed up to make up for the time lost. So this presentation is really about sort of integrated protection and condition monitoring for offshore wind systems. So I want to start this presentation by sort of setting out what I think are three main challenges that I see, which I think are sort of barriers for effective offshore wind monitoring systems. So first, it's very challenging to organize visits to offshore assets, and there are kind of obvious health and safety risks with that. So unnecessary visits should be avoided wherever that can be achieved. Second, conventional SCADA-based monitoring systems, they will usually not provide a lot of granularity, and they can miss certain transients that might be important, unless there's dedicated power quality monitoring or digital fault recorders already installed, which is uncommon at the moment, certainly at individual turbine level. There may only be detailed measurements available at the grid connection point. So there's no way of seeing in real time if an individual turbine is misbehaving in certain ways. And the third thing is, I think it's a major kind of hidden risk that's sometimes overlooked. So if you cannot time align your measurements, then you can't really expect to, sorry, this is still advancing on its own. I'll try and deal with it. So I just wanted to stress here that the time alignment of measurements is very important, because otherwise you can't really perform useful or meaningful analysis of the data and correlate the different parameters, or you might end up wasting a lot of time just patching up the data so that you can put it into time sync, first of all. So I hope to show you a route that can help to solve these challenges. So just to kind of introduce Synaptec, so we are a vendor of sensor systems based in Glasgow. And what we've created is a unique passive sensing technology, and that allows CTs and VTs and other sensor types to be bonded to an optical fiber. So this means that we can capture many distributed sensors with a single fiber, and then deliver the data, the measurements, to a central location wherever it's needed. So this is quite versatile, and we've worked with several grid operators and also in offshore wind to deploy this type of solution. So what does it look like? So this slide shows how a single optical fiber can visit many different assets, potentially over a long distance, and capture multiple sensor outputs. So, and all the sensor measurements are delivered to the central location. So we use a unique method to passively interrogate each sensor using light, and so far, that includes many different sensor types like voltage, current, strain, vibration, and temperature. So, and normally we can deploy 50 sensors per fiber over typically 100-kilometer distance, although we can increase the distances in certain cases if the quality of the fiber network is good enough. So what this means is that at each sensor location, there's no need to have a power supply or batteries to replace, or any additional communications equipment, or any other additional infrastructure that you might normally need like, sometimes you might need to build an entire substation. So we avoid those kind of that kind of infrastructure. So how is this applied to offshore wind? Well, as this slide shows, one or more of our systems can monitor every turbine in a wind farm, and we can be looking at multiple different parameters, voltage, current, or mechanical. So what we can do is we can rapidly respond to electrical faults and identify faulted cable sections. It's very trivial, basically. We can provide things like thermal alarms for the cables. And also we automatically provide power quality analysis of all our electrical measurements. So that's kind of built in at the individual turbine level. So recently we partnered with the Offshore Renewable Energy Catapult in the UK to install our system in their test site, which is at Leavenmouth, as you can see on the screen, on the east coast of Scotland. So this is a 7 megawatt wind turbine, but it's a real generator. It's grid connected, so it's a quite a valid test of our system. So what this looks like is we have our interrogator unit, which sits in the substation in the SCADA room onshore. And also onshore, we have 3 current sensors bonded to the fiber. And then offshore, we have another set of current sensors, and we also have 4 temperature sensors that are strategically located inside the turbine. So here you can see the installation. It's a little bit messy, but you can see there's no power supplies or anything else, or copper connections. There's nothing there additional we had to install. It's just the CTs and the optical fiber. In the lower right, you can see the temperature sensors just barely in there, and they are designed to, in this case, to measure the temperature of the cable terminations, which is a common kind of hotspot that can lead to some problems. And we're also measuring the ambient temperature too, just for a reference. I'll also mention that we're already preparing to deploy a follow-on project at the European Offshore Wind Deployment Centre at Aberdeen, where we'll kind of scale up the solution and monitor more turbines with more sensors. So how can we sort of achieve the intelligence that's required, to get to the point where we can do sort of things like predictive maintenance, so we can actually help reduce costs and reduce the number of trips offshore and that kind of thing. So really, I've joined Synaptec about a year ago to work on this, and so I've been looking at taking the unique features of Synaptec's physical hardware platform and trying to exploit it fully. So the platform has the ability to see far and wide, but we don't compromise on measurement quality. We always extract data at the full sampling rate and allow it to be archived. So this allows us to target solutions in different timescales. I'm battling against the automatic slide advancing here, but so the first timescale is the kind of really time critical, sub-cycle protection functions, which we can do and we've demonstrated in the past. In more human timescales, we can provide the information that's needed for real-time thermal rating of cables. We can do things like oscillation detection quite readily because we see the full waveform, and we can see every single frequency that's going on there. And in the longer term, we can also kind of offer a new sort of dimension in terms of asset management. Again, because we can see the full waveform in detail for every asset that we're looking at, and we can look at that asset in both electrical and mechanical ways together. So rather than just sticking with some more PowerPoint, I thought I'd show you what this actually looks like. So this is some screen captures for software which I recorded recently. And again, it's pre-recorded, but this is of our actual system deployed in Leavenmouth. And you can see it sort of geographically there. Here you can see a summary of the kind of key measurements that the system is recording. And this is just sort of summarized for, like an engineer would perhaps want to see. So we can see, synchrophasors that we're calculating from the current measurements, summary of the temperature measurements, and some other things like total harmonic distortion and the measured frequency, which is keyed off the current. But because we're recording the full waveform, we can zoom in to every individual sensor and see exactly what's going on. So we can always see the full waveform for currents and voltages, at least at 4 kilohertz sampling, although we can go much higher than that if needed. At the other end, as well as like the sort of low-level detailed measurements, we also capture the trends over time. And in this case, you can see several months of data, which we've captured at a 1 second granularity, although we could do that faster if needed. So here you can sort of visually correlate different parameters. You can see the sort of obvious relationship you might expect between wind speed and power output. And you can do that visually here, but there's also APIs where you can sort of do that more automatically. So far, this was a relatively basic installation with only 10 sensors. But here you can see how it can scale up to many different deployments, each with many different sensors of different types, and including sort of custom visualizations for different specific applications. So it's quite versatile. In terms of how we deploy it, it's again very flexible. Typically, it's going to need to be installed within a private sort of secure network, but we can support that. Or of course, we can simply provide the raw data to existing systems if that's what's needed. So coming to the end here, and I just wanted to just highlight one last thing really, is that the system always observes every sensor at a very high fidelity and sampling rate. So that means we can stream and archive the full electrical waveform data, or continuous point and wave data as it's sometimes called. So first, that means that we can perform power quality monitoring, as I mentioned, and that's quite important in many situations, including offshore wind. It also means that, for example, we can see every interesting or important transient for every asset that we're monitoring. So, for example, this could be a detailed record of every arcing event that's experienced by a circuit breaker over its lifetime, which is typically a very long lifetime of several decades. So, this opens up a new approach to condition monitoring where sort of finally there's enough data to make intelligent decisions about asset performance over time and maintenance of that asset. So, or more realistically, now it might be to train a machine learning algorithm to do that automatically. So just to finish up, I mentioned sort of 3 challenges at the start of this presentation. And so hopefully I've shown how we have a route to solving that to some extent. So first of all, we provide a passive sensing technology, which we believe can be exploited to enable predictive maintenance. As I said, each sensor measures at least a sampling rate of 4 kilohertz, so we can see everything an asset experiences in multiple dimensions in real time. And we also make it easy to analyze our measurements and gain an actionable value because everything is inherently time synchronized. It's just automatically done as part of our system. So just in summary, this is a solution that's inherently secure and is fit and forget by design. And we can push data where it's needed immediately. And the data is composed of a sort of unique package of electrical and mechanical sources. And it's worth mentioning that this is can be achieved with a relatively sort of tiny carbon footprint because it's a passive sensing technology. So I'll stop there, but I'm happy to speak to anyone about this. So thank you very much for listening.
Excellent, thanks, Stephen. We'll just leave action with you for the moment, and then I'll steal it off of you once you've answered a question or two. Actually, I'll just share it with you right now. Yeah, so Oh, I've lost it. Yeah, so you mentioned that Synaptec's synthesis feature sort of helps the asset owner in understanding potential for necessary maintenance. Like, do you release the software like in tiers? So like, say as an asset owner, could I just say own the base Synaptec software and then be able to access the data myself for me to do my own data processing through that API that you mentioned? Or does it all come as one?
That's a good question. I hadn't really thought about that. At the moment, it just comes as one thing. We don't really distinguish, and you can use the kind of web-based user interface if you want, or you can access the data through an API if that's what you need, and it's all built into one thing.
Cool.
That makes sense.
Okay. Yeah. Maybe one more quick question, and then we can move on. Do you provide? You said about local server systems that it would connect to store the data. So, are you expecting the asset owner to already maintain and own these server systems, or is that something that you provide as well?
We can do that. We can help absolutely set that up if that's what's needed. We can deploy it in the cloud if that's preferred, or we can do it within whatever's available. For our next deployment in Aberdeen, we're, for example, the owner there is helping us set up like a virtual machine to install the system there. So that's how we do it.
Okay.
In that case.
Yeah, that's really interesting. There's so many routes you can go down. There's a lot of potential with this. It's really, really interesting. Yeah, thanks for that, Stephen. That was class. That was great. Right. So right up next we have Dr. Jen Lee. If you could share your screen.
Okay, let me check. Share screen. Can you see now?
I think it's just loading.
Okay.
Yes, we can see that. Okay, the virtual floor is yours.
Because I already pre-recorded. I don't know whether the sound will be transferred later as well. Let me try. Can you hear it?
Yep. Oh, we can hear you, but
not from the video?
Not from the video, no.
Okay. Do I need to set something to?
I think that's on our side.
So when you share your screen, there's an option says also share your computer audio. So you probably need to tick that box.
Yep. Similar to the Microsoft Teams. Sound.
Hi everyone, this is Lee from Cardiff University. I'm very delighted to be invited for this CIGRE NGN UK and Denmark joint webinar. In this webinar, I'm going to present citizens European HVDC and offshore wind.
Sorry again, can I interrupt? I don't know if it's the case for everyone else, but I can't actually hear or see what's going on.
System.
Could you pause that again? Sorry.
Firstly.
Excellent. Okay. So I think you might have some bandwidth issues. The solution is that I also have the pre-recorded version on my laptop. I shall.
Okay. Yeah, maybe you can play it.
Yeah, we'll give that a shot. One second, folks.
Hi everyone, this is Jingyi from Cardiff University. I'm very delighted to be invited for this CIGRE NGN UK and Denmark joint webinar. In this webinar, I'm going to present the latest development and challenges of this European HVDC and offshore wind system. Firstly, let's start from the state-of-the-art of this HVDC and offshore energy system. As we know, our Earth is facing this global climate changing, and all the governments around the world are setting their own goals and targets to achieve this sustainable development. For EU, previously we set this target 2020 for 2020, and now we already arrived this year and we have new goals for the 2030. For example, we want to achieve 32% of this renewable energy in this total energy consumption, and 32.5 improvement in the energy efficiency. And if you read different reports, you can commonly see this 40% gas emission target for EU countries. And for the UK, we already set this ambitious target to achieve net zero emissions by 2050. And the National Grid UK said that they can achieve this pure zero negative by 2025. And recently they announced that they can achieve this carbon negative by 2033. And the most important solution to achieve this energy transition and this sustainable development, the renewable energy is one of the most important solution. And we also know this wind energy is one of the most important renewable energy technology. And you can see from this figure, the onshore and offshore wind installed capacity in European 28 countries already achieved more than 200 gigawatts. And you can see UK ranks the third and followed from Germany and Spain. But for UK, it's the largest offshore market in the world. And in the last year, the wind energy already occupied 15% of the total EU consumption. So this is a great achievement, but we want to improve them more. So we know wind energy is a free and renewable source. And why we want to use this offshore wind energy? Of course, it is obvious we can build this wind turbine in the sea, and this wind is much more stronger than this onshore wind, and therefore it will be more stable. And in the area of the sea, we have free zones. We can build these wind turbines and wind farms. But for this onshore system, because we are lacking of the land, this is not easy to do that. And we have these benefits, but we also have these disadvantages as well. For example, it's difficult to design these offshore wind turbines, and the operating environment is much more severe compared to this onshore, and the maintenance cost will be higher. So this is the part we want to achieve them better. This figure shows the location of these UK's offshore wind farms. Thanks to this development of this round 1 to 4 in the past decades, we already achieved this 10 gigawatts offshore renewable energy, wind energy. And in the future, we want to have more than 30 gigawatts for this offshore wind system. And this will play a significant role in achieving this 2050 net zero target. For these offshore wind systems, we can use the conventional HVDC system, but for this submarine cable, it has this problem of the cable capacitive charging effect. So if you want to have a long distance, you may this use this reactive power compensation station. For example, in this housing HVD offshore wind system, we use this reactive compensation station to achieve a long distance transmission. But for this HVD system, we do not have this limitation, and if this distance is beyond 80 kilometers, this HVDC will perform better in terms of the capital cost and also for the flexible control of these HVDC converters. And then I will present the challenges for the future development. For example, this HVDC is very good. It cannot be only used for this renewable energy integration. It can be used for this transnational and national connection. For example, there are already many links from this UK and with his neighboring countries. And the next logic step is to build such kind of large-scale HVDC system. For example, this is the concept of this supergrid. And using this kind of supergrid, we can achieve much more higher energy efficiency and more reliable. And we can compensate the different source and load. For example, using this hydro to be a kind of energy storage. And there are wind turbines and the PV panels. We can connect them all together and to achieve a better power system. But we are facing this challenge, as I mentioned in the previous slides. The manufacturing and the construction and the maintenance for the offshore wind system is very difficult. As you can see, if there is a fault, you may send people to the wind turbine using the helicopter or a ship to maintain this and or fix the fault. And also for the construction, if you have bad weather, you will lose a lot of money for this construction. So they are very important challenge. We need to solve them. Another thing is this submarine cable manufacturing. This can be used for low sea and deep sea for this HVDC transmission, and also for the manufacturing. And you can see the laying is difficult as well. And if we want to have a higher power transmission, we need to build them in higher voltage, but that is not easy, and we need to improve them step by step. The other thing is these converters. Thanks to the development of these semiconductor devices, for example, the IGBT, the voltage source converter is becoming more promising. But for the existing LCC, it still have the benefits. For example, the cost is low and the losses is low as well. So we may combine them together to form this kind of hybrid LCC HVDC system to use their benefits. And also another challenge is to build the DC transformer, which is used to connect different HVDC system with different voltage levels, or which systems are built in different decades. But for this manufacturing, in the research papers, there are a lot of topologies and designs. But for the manufacturing, it's still facing the problem of reliability and the cost and the power losses, and also whether it can be used for the fault protection, because this fault isolation for semiconductor devices is difficult because these devices are sensitive to the surge current. So we want to solve it better. And also we may use this diode rectifier HVDC system to achieve a low-cost offshore wind system. And one of the most important challenge is this HVDC protection. This is one of the bottleneck limiting the development of HVDC, because this DC current is not easy to be isolated, and the DC arc is difficult to be interrupted because there is no zero crossing. And the conventional AC system protection cannot be directly borrowed to these HVDC systems. We may design some special methods, for example, the handshaking, open grid, or some traveling wave based, but it still needs efforts to be in this area. And also the design of the DC breakers, they are still very expensive. Although there are some applications in China, but for EU, we still do not have real applications in the field. And we need to make efforts to reduce the cost and improve the reliability of these DC breakers. And it will be used for the future large-scale HVDC connection. And another thing is that we do not have this HVDC grid code. So for the regulation, the operators, transmission operators still need to design these DC grid codes to achieve this energy system transition, and also to achieve reliable and secure operation of this HVDC system in the future. Okay, thank you for your time. Bye-bye. If you have any questions, please feel free to ask. Thank you.
Okay. So, yeah, Zoom wouldn't let me multitask there, so I could not compile questions. I shall check if you have questions. Give me a second.
It seems no. I can see this chat box as well.
Well, I think as you were mentioning HVDC and HVAC again, obviously cable faults are a bigger issue when you're moving towards HVDC. So I suppose, what are the main ways that you see the industry moving towards, like, mitigating or detecting such faults?
Okay. For the research in the academia, there are many papers investigating these kind of questions, detect the fault in the HVDC cables, because most of the case, the cable is more secure and is safe because it's not like the overhead line have common faults. There are different methods, for example, using the traveling wave based to detect the fault and discrete the fault quickly within several milliseconds. But I think most of the applications at this stage are in the papers. In the real applications, I'm not sure they are applications. And the EU projects like promotion, they make a lot of efforts in this DC fault detections, both are in this overhead line and the cables.
Okay, yeah. And obviously there's a lot of work being done to try and research new control and protection methods for HVDC, but do you know if there's any research that's underway that's sort of trying to reduce the necessary processes for HVDC? Because, I mean, you can go about just trying to solve all your problems, but if you try and cut it at the source, that might even be better. Do you know if there's any research being done like that?
Okay, yeah, there are a lot of research in this area, and also in China, they already have this 3-terminal and 4-terminal HVDC network, and the grid. The Zhangbei 4-terminal is a 4-terminal, and also the ongoing one is the 3-terminal Kunlun project to combine this LCC and the VSC. Both of these projects are real projects. They developed this kind of protection, including this kind of using DC breakers and also using the full bridge or half bridge and full bridge MMC to control the fault current to reduce it to 0. So there are different methods. And also in the initial stage for this Zhoushan project 5-terminal, because AC was the first 5-terminal one, and the AC is using this AC breaker-based protection. So you can see in China, there's different projects that already use different protection strategies, including this AC breaker, DC breaker, and also the converter control. So there are different research and real application. But in EU, we do not have this DC grid yet. So it's still in the research stage.
Okay.
Yeah.
Excellent. Okay. I think we're getting some new messages coming in.
Yeah.
So it's just Stephen answering back. Yeah. Okay. So I think that's all we have time for anyway. I think we're slightly overrunning, but that's absolutely fine. Hopefully it's all right for everyone else. Yeah. If everyone can just see that, I'll just use that as the closing slide.
Okay.
Yeah. Thank you again. Thank you very much.
Yeah, no problem. Okay. Thank you.
Cheers. All right. Well, yeah, just to round that off, I found that really interesting. If there was any other extra questions that you would like to ask any of the speakers on any technical matters, or any to do with the NGNs, please get in touch with myself or Daniela. Yeah, I think that's all. Again, I'd like to make a special mention for those that were involved in setting up the webinar today. Thank you very much to the speakers for giving us your time and your effort in pre-recording the presentation as well. That seemed to come in handy. And also, yeah, thank you to Daniela, Xian and Janning as well, and everyone else behind the scenes. I think it was a reasonable success. Okay. Yeah, all right. Thanks very much, everyone. Hope you all have a good day.
Thanks, Max. Thank you. Bye.
Cheers.